Good morning, guys. Welcome to the class of CE331 Environmental Engineering 1. So, we were discussing water requirement, and today we will discuss demand forecasting. We'll start from demand forecasting. So, what happens that in a community, when you design water supply system for a community, for example, this is the community here. That's the community. Now, if you want to design a water supply system for this community, then first of all, you need to know what is the demand, Q demand, am I right?
Yes, sir.
Now, this Q demand, this sewer network, and I'm sorry, this is water supply network of pipe. This is costly, so you don't design it for 1, 2, or 3 years. You design it for a long time, for example, 20 years or 30 years or even 40 years. So the thing is that the population today may not be similar to the population 20 years later. Am I right?
Yes, sir.
So, and population directly correlates with the demand of the water. So, when you design the water supply network, then you have to design it for the demand after 40 years. Okay, so you need to know what would be the, if your design year is 30 year, then you need to know what is the demand of the, what is the population or water demand after 30 years. It can be population or it can be Q demand, whatever you want. So Q demand varies. Usually with time it increases. Okay, usually with time it increases. So you need a model basically. Okay, and you can see this increase is not linear, this is non-linear, and this follows, usually, I mean, sometimes you can assume it's linear. That's why you have a linear model, that QIN means Q30, and QI means present water demand today. Okay, here 1 plus n is the number of years later, your design life, for example 30. Okay, and A is the rate of population growth. A is the average annual population growth during the design period. Annual population growth, that means each year how much population is increased in percentage. Is it clear?
जी सर.
For exponential
Yes, sir.
model, we are looking for an exponential here. This is the exponential model. This is a linear model. Here assumption is linear. Here it is exponential model. Okay. By the way, here you have time, right? In years. So in exponential model, you can see that QIN, that means future demand, Q30 basically, Q30 or Q20, Q40, whatever it is. QI is Q today, present. You can call it present. Q present, and A is the, as I told you, average annual population growth. Average annual population growth, and N is what? In his design period, that means 30 or 40, whatever it is. Okay? So let's solve some problem here. In a residential area, 250,000 inhabitants, the specific water demand, that means Q average, is estimated at 150 liter per capita per day. That means Q average is given, Q average, liter per capita per day. But you need to have Q in liter per day. Am I right? Hmm?
Yes, sir.
So Q average will be, you have to multiply this, 150 has to be multiplied with what? The capita,
250,000.
250,000. 250,000. Then you'll get it in liter per day. You'll get it in liter per day, right? Right, guys?
Yes, sir.
Okay. Now, if you wanna convert it to meter cube, then you have to divide it by 1,000. 150 into 250 K divided by 1,000. That means your liter becomes now meter cube. Now per day, if you want to convert it in per year, then you have to multiply this with 365. It's easy. I mean, in one day, the demand is Q. Then in 365 days, that means 1 year, the demand is Q into 365. Am I right?
Yes, sir.
Yes, sir.
That's why we are multiplying it with 365. So you get what? 250K into 150 into 365 divided by 1000, and that's how you get per day will be per year, meter cube per year. Okay. Calculate the demand in 20 years time. That means your n equals to 20 years. Design period is 20 years. Annual demand growth is 2.5%. So A has to be in percent, right? 2.5%. Okay. So you have to do it both. You have to do it in both linear and exponential model. So look at the linear model. This is the equation. So what is QIN? You have to determine this. What is QI, guys? QI is this. What is this value? 91,250, right? 91,250. Are you following me, guys?
Yes, sir.
Yes,
Yes,
sir.
sir.
Then
Yes, sir.
1 plus N. What is N? N is 20 and A is 2.5. So N is 20 and A is 2.5 divided by 100. Can you please calculate the value here?
136875.
No, it should not be that low. 2.5 divided by 100. It should be a much larger value because, clearly this is greater than 1. So
Sir, 136875.
1, 3, 6, 8,
875.
7, 5. So it was 91,000, 91K. Now it will be 136K. 136K, right? 136.8K or whatever. Am I right?
Yes, sir.
Yes, sir.
Now, um, if you apply exponential model, then let's write it again. Qi is 91,250 into 1 plus A is 2.5 divided by 100 to the power n. N is 20. Now tell me what's this value? 1 plus 0.025. That means 1.025 to the power 20 multiplied by this 1.025 to the power 20 multiplied by this.
So 79 lakh 7914675.859. 7914
7914
675
675
0.859.
স্যার আমার
point
স্যার
whatever it
আমার স্যার আমার আসতেছে 149,523।
okay 149,523. So this is 149k. So you can see that 149k. So these two values is not exactly similar. This is 136k and this is 149k. So there are some dissimilarities, right? Because the model is different, linear model and exponential model. Usually, naturally, the population growth follows exponential model. So we may assume that this is the correct one. And of course, what was the unit of this one, guys? Remember, meter cube per year.
ইয়ার।
Why the unit of this will also be meter cube per year and meter cube per year. Okay, which is approximately 50% compared to the present demand. Okay.
Yes, sir. Sir,
Yes.
the value of Q average মানে স্যার কিউ এভারেজের ভ্যালুটা মিলতেছে না আমার এখানে যেটা আসছে 91,000।
Okay, whatever you get, that's the value. You don't need to have an exact matching with this one. You need to
ওকে
make
স্যার।
sure you understand this thing. Okay, they make they might made a mistake. That's okay. Okay, just understand the mechanism. Whatever value you get, you use it over there. No problem. Okay,
ওকে
so now that's the end of the water requirement.
স্যার, why exponential graph is used? Why not linear one?
As I told you that naturally, naturally, if you draw, for example, from 1990 in Bangladesh, for example, if you draw up to 2010, you'll see the population graph, of course. You'll see the, I mean, if you put these points, you have the data, right? You have the data, am I right? So if with the data
Yes
you
sir.
plot this, you'll find this exponential in majority of the cases. Population
Okay
of,
sir.
because these two are correlated. So this is the nature. Okay, this is the nature. Sometimes it's unusual, although might be linear, but majority of the cases it is exponential. Majority of the process nature follows exponential model. Okay,
Okay
can
sir.
be decreasing This is also exponential, is increasing, negative slope and positive slope. Okay, clear?
Clear,
Yes.
sir.
Okay, pumping machineries. You know, we have to use pumps for a multitude of reasons. For example, to extract water from aquifer, to supply water to an elevated location, right? So I will discuss very briefly about the pumping machineries. So if you there are numerous types of pumps. If we classify them, we can classify them based on the class of service. We can classify them based on the form of motive power. That means how the pump is getting the power. And we can also classify them based on the mechanical properties of operation. That means the mechanism that is occurring into the pump. First of all, class of service. If we classify or divide them, we will get deep well pumps, which extract water from a deep tube well, from a deep aquifer. This is deep well pumps. One is low lift pumps, and there is high lift pump, booster pump. You know, if you have a low pressure in a pipe, you can apply a booster pump to increase the pressure. Is it clear?
Yes, sir.
Standby pumps. For example, you have a pump already here. Now you also have a backup pump here, because if this pump fails, then you can use this pump. So this is called the standby pump. This one is called the standby pump. Fire service pump. Of course, to in case of firefighting, you need to reach a elevated level, so you need a pump. The pump that is used in firefighting, that's called fire service pumps. Okay.
Sir, high lift pump আর ফায়ার সার্ভিস পাম্প দুটো কি সেম?
Kind of similar, yes.
ওকে স্যার।
Form of motive power. Sometimes pumps can be electrically driven. Pumps can be diesel driven. The fuel can be electricity. The fuel can be diesel. The fuel can be gasoline. The fuel can be steam engine. The fuel can be solar. Okay. Mechanical principle of operation. Displacement pump, centrifugal pump. In centrifugal pump, you know, um, if something rotates, then there is a force that is outward the center. Am I right? Centrifugal force.
Yes, sir.
So in centrifugal pumps, they use this force. They rotates and use this force to suck or pump the water. And this rotation can be right-handed, left-handed, etc. And it can also be jet pumps. Okay, so if we just focus here, class of service, you have the definition: deep well pumps, deep well, low lift, high lift, and others. So deep well pumps operate in tube wells and pump water into service reservoirs or directly into distribution system. Low lift pumps operate for small heads, because this is low lift. such as at treatment plants for pumping water from a storage tank to an high elevated tanks. For example, from here, you want to elevate it to a small elevation, to an elevated tank. Then you can use these low lift pumps. High lift pumps are large heads as for pumping water from clear water reservoirs into the elevated tanks or directly into the distribution system. Sometimes you see large tanks, right? Don't you see?
Yes, sir. Yes, sir.
Maybe 30 or 40 feet, or maybe higher, maybe 60 or 70 feet, maybe 100 feet. So you use a high lift pumps for this to lift the water. And then booster pump, I already told you. Standby pump, I already told you. In case of temporary shutdown, you need a backup. That's a standby pump. And pumps for fire services. Okay, I already mentioned it. So that's it. Now we'll talk about the well design. So in from an aquifer, if you want to extract water from an aquifer, if you want to extract water, then you need to inject a tube here, right? Let's draw it again.
Yes, sir.
And for example, this is the ground surface. You have aquifer here. For example, it's an unconfined aquifer. So this is the aquifer. So you need to inject a tube. Now, first question is how deep you will go inside the soil. To know that, you need to know that you need to know first of all you need to know the location of the aquifer. Am I right? If you know
Yes, sir.
the location of the aquifer, then you'll be able to identify how deep you will go into the soil. Okay, so that's your first task. And to do that, you need to how do you do that? Okay, I'll tell you after 2 minutes break.
Okay, sir.
Okay, guys. So to design the tube well, are you following me?
Yes, sir.
Sir.
First of all, you need to know the location of the aquifer, and then once you know the location and the aquifer, then you will know how deep you will go into the soil, and then you need to extract the water, right? Now, how do you extract the water? Remember that you have soil particle as well as the water here. Your objective is to extract the water, not the particles. For this reason, you need to, this is the water, right? You need to extract only the water, not the particles. So that's why you need to have a screen here. That means it will have some openings, and these openings will allow only the water to pass through, but will stop these particles to enter. Am I right?
Yes, sir.
So you need a screen on so that the only water is extracted. And you need to design the size of the screen. And the size of the screen will be determined based on the size of the particles, right? Because your objective is to capture the particles. I mean, soil particles. Are you following me?
Yes, sir. So,
Yes, sir.
so in the previous classes, you told that we design some small particles beside the tube.
Right. That's
Um,
called gravel pack materials.
yes, sir.
Yes. And that's why that the screen we for better efficiency we design, if this is a screen, for better efficiency what we do is we want, um, if we have this here, um, let's draw it here again, right? Now we have the screens and it has the openings. If I want to show you the real picture, let's show it here. This is the screen. Did you see?
Yes, sir.
Right?
Sir, how do we get to know the size of the particles deep inside the soil?
Yeah, yeah, that's what I'm going to show you. It can be of many shape. So if we go there, if we look at the particles, so here is the gravel pack material. Okay, here is the gravel pack material. Now the thing is, here you have the soil particles. Okay, what we try to do is we want to have a gradual transition, a gradual transition. Okay, that's why we this is a soil particle, and we extract the soil surrounding the screen. We extract the soil here, and we put some lab made materials or materials designed by us or the engineer here, so that we can have a gradual transition of the size of the material. Okay, for example, um, smaller, smaller, larger, larger, larger. Or if I draw it correctly, let's we want to have a gradual transition of the particle. So what we will do here is we will go step by step. First of all, we will design, we will identify, we'll see how to identify the location of the aquifer, and then we will design the size of the screen. And in that step, I'll show you in detail how to use the gradation curve, grain size distribution curve to determine, to design this gravel pack material. Okay, and how to determine, how to vary the size of the particles gradually. Is it clear?
Yes, sir.
Yes, sir.
Okay, so now let's go back to the well design. So tube well can be of many shapes, like shallow tube well, deep tube well, deep intermediate tube well, and deep tube well. So shallow tube well may have different categories like hand pump tube well, rower pump tube well, disco pump tube well, and many others. Okay, so you see that this is a disco hand pump tube well, and if we see the different parts of the tube well here, it's a hand pump, so you need to manually handle this. Okay, so this is the ground surface, for example. So this part is above the ground, and this part is inside the ground. Now, starting from the base or the tubal upper part, we see that we have, first we have the casing. This is the casing. Okay, then we have a piston. This one is the piston. As you move the handle, the piston moves upward and downward. Okay, you have a foot valve here. This is the blind pipe. Okay, and then you have a strainer. This is the strainer, and then you have the sand trap. What is sand trap? I will discuss it. Blind pipe. Pipe used between the screen and the hand pumps are called blind pipes. So between the screen or strainer or screen, same thing. You guys, are you following me?
Yes, sir.
Yes,
Pipes
sir.
which is between the screen and the hand pump and the hand pump. You may call this blind pipe. Okay, and then you have strainer. I already told you this is the strainer. So screen, what is the screen? It's a perforated portion of a well through which groundwater enters from the aquifer. In Bangladesh, 38 millimeter diameter strainers are used for hand pumps. So in Bangladesh, for hand pump in Bangladesh, we usually use 38 millimeter diameter screen. That means this strainer. Now these strainers are usually 2 meter long, but it will be final length will be determined by our design. You'll see. And can be made of steel or PVC. The openings are 0.008 inch or 0.01 inch or 0.012 inch. That means these openings, we are talking about these openings. Are you following me, guys? These openings, this
Yes,
one,
sir.
Yes, sir.
usually 0.01 to 0.01, it varies. Okay. Sand trap. You know what happens that even though you have designed this screen to capture the soil particles, some particles still may enter here with a very slow rate. Now, years after years of this phenomena, what would happen? You'll see they are depositing inside. Am I right?
Yes, sir.
Now, if they are deposited inside, can the water enter from there?
No,
No,
sir.
sir.
So, what we do, for example, in 20 or 30 years of design life, maybe the deposition height will be this. So, what we do at the initial condition, at the beginning, we give a solid pipe here. We don't give a screen at the bottom. Okay, so this is a solid pipe. So, whatever material enters here, that gets deposited here. Clear? That's the sand trap. So the sand trap is an extension of a blank pipe of about 4 to 6 feet long, depending on the depth of the tube well. So 4 to 6 feet long. This can be 4 to 6 feet long. Clear?
Yes, sir.
So the sand trap provides a repository, that means a location for sand entering the well and ensures that the screen itself is not blocked. The screen itself is not blocked. Clear? So we don't want the screen to be blocked. That's why we use sand trap. Clear?
Yes, sir.
At least until the sand trap is filled. Now, the question, as I told you that aquifer usually have the larger particles than the other part of the soil. Why? Because if you want to have water, then the size of the particles has to be larger because larger pore exists in between the larger particles. Am I right?
Yes, sir.
Yes, sir.
So did you see the pore size very small, but the pore size here is very large. So if you want to have water, you need to have coarse particle. Coarse means larger. Coarse. Coarse means larger. Am I right? So for example, we see that we have a soil layer here, clay, fine sand. Fine means a smaller particle. Coarse means larger particle. That means aquifer are aquifers are expected to be in this layer, right? Let's call this is the aquifer. This is the aquifer. So what will be the screen position? Of course, you need to. This is a screen. You need to locate the screen in the aquifer. Am I right? So you see coarse sand, aquifer. Coarse sand. Here is aquifer. Coarse sand. Here is aquifer. Would you put your screen here in the fine sand? No, right? You need to put it in the coarse sand. Are you following me, guys? Wherever you
Yes,
get
sir.
Yes, sir.
the, wherever you get the um, water or aquifer. So to design a well, first of all, you need to know the length of the screen, diameter of the screen, slot opening of the screen, screen size, gravel pack material, yield or transmission. Yield means the Q of the tuber. Yield means the Q of the tuber. And length of the casing pipe. Length of the casing pipe. So as I told you, the first task is to identify the location of the aquifer. That means most productive aquifer. That means most productive means the most productive aquifer means the aquifer which produces the highest number. I mean highest amount of water. Okay. So the intake portion of the well, that means the screen, must be placed in those zones having the highest hydraulic conductivity, which is determined using the following technique. Hydraulic conductivity means what, guys? Conductivity means the properties of the soil which allows the water to pass through into into it. Okay. Higher hydraulic conductivity means the water can easily pass through. Lower hydraulic conductivity means the water cannot easily pass through the soil. Okay.
Okay, sir.
That means the aquifer will have the higher hydraulic conductivity. So what we do here um, is this. First of all, we need to know one property, and this is d60 by d10. What is d60 by d10? If uh, before I go there, I need to ask you something. Did you perform the grain size distribution curve,
Yes, sir.
Yes, sir.
right? And from there you generate this curve, right?
Yes,
Particle
sir.
minor, and here is the particle size, right? What happens that you have sieves. Here is one sieve, two sieves, number three, number four, many sieves, and you have the soil here. So you shake it, and different sieves have different opening size. So you will get captured this different size of the particle here. So this is retained, right? Captured, so retained. So number 16, which has fifth size is 1.18 millimeter, number 30 is zero point 0.6 millimeter, and similarly the others. Finally, you have the pen at the bottom. You have the pen at the bottom where the rest of the material will be stored. Materials retained. So, for example, the mass this. So this is the retained, right? Am I right?
Yes, sir.
So what is the
Yes, sir.
total? Total is the summation of all of this. You get 99.6. And percent retained. Percent retained is what? Easy. 0 divided by 99.6, 0.2 divided by 99.6, 16.4 divided by 99.6, 40.4 divided by 99.6. This is what? 40.4 divided by 99.6. Are you following me?
Yes, sir.
35.54 is what? 35.4 divided by 99.6. Cumulative percentage return. What is that? That's basically 0, 0 plus zero point 0.2, zero point 0.2 plus 16.46, 16.46 plus 40.56, 16.67 plus 40.56. That becomes 57.23. Are you following me?
Yes, sir.
Yes, sir.
Similarly, this. So you already know these things from your previous lectures. So I'm not going into detail of these things. And finally, percent finer is what? Percent finer is 100 minus this. 100 minus point 2. 100 minus 66, 100 minus 16.67. Okay? 100 minus 57.23. এটা basically integer নাম্বারটা নিচ্ছে। That means 100 minus point 2 মানে কত?
99.8.
99.8.
99.8. So এটা integer. Next nearest integer টা নিয়েছে। So this is 100, approximately 100. And this is what? 100 minus, so 100 minus 16.67 is around 83.
83.33.
Yeah. Okay. So that's how they have done it. Now, what is fineness modulus? Can you remember what is fineness modulus? This is the equation. Fineness modulus is percent cumulative retained of standard sieve size. Not all of the sieves. Remember, the standard sieve size. And what are the standard sieve size? 4.75. We don't have that. 1.18. Before 1.18, we are supposed to have 4.75. We don't have that here, so that's okay. 2.36, we don't have that. 1.18 millimeter, yes, we have that. Zero point 0.6, yes, we have that. Zero point 0.3, zero point 0.3, not 0.425 and 0.15. So these standard sieves you need to consider for cumulative percent retained. So cumulative percent retained, tell me what is the value? This is for 1.18, it is 0, right? Let's do it here. 0 plus for zero point 0.6, this is what, 0.2. For 0.3, this is 15.723. Are you following me, guys?
Yes, sir.
Yes, sir.
And for 0.15, this is 92.77. Divided by what? 100. Can you please tell me the value? Can you please tell me the value?
Sir,
1.502.
1.502.
So
502.
1.02. This is
Sir,
one
why you didn't take 98.4?
98.4. Why would I take it? Because this is not a standard ship size.
Oh, okay, okay, sir.
That's what I'm doing. That I have marked all of them. Why? Because these are standard ship size. Anyway, so 1.502. This is the fineness modulus. Now, my question is, what does this fineness modulus tell you? This tells you, look at this. What is this basically? This is cumulative percent retained, retained. That means higher the FM, higher is the percent retained, and higher is the percent retained, larger is the particle size. So FM higher means particle size higher. Clear?
Yes, sir.
Yes,
FM
sir.
high means particle size high, larger particle. So FM of coarse aggregate is higher than the FM of fine aggregate because fine means smaller, coarse means larger. Now, if we draw the grain size distribution graph from here, in y-axis you put percent finer, and in x-axis you put particle size. That means this is the particle size for corresponding to this percent finer. Now you'll get this graph. Now what does this mean? This means that percent finer. What does this mean? It means that 43% particle, 43% particle are smaller than zero point 0.3 millimeter. Am I right? Why smaller? Because finer. Because they have passed it. They have passed it. They have passed it. And when a particle passes through a screen, when this is smaller, right?
Yes, sir.
Yes, sir.
So that's why percent finer, zero point 0.3 millimeter size, it has 43% finer. That means the 43% particle of the aggregate is less smaller than zero point 0.3 millimeter. Similarly, 7% of the particle is smaller than 0.15 millimeter. Anyway, now let's go back to the uniformity coefficient. We can have a parameter that is d60 by d10. What is this? d60 is the size of the particle corresponding to 60% finer. That means 60% finer size is what, guys? This is point 1, this is point 2, point 3, this is point 4, 0.35, something like that. And d10 is the particle size corresponding to 10% finer. That means point 0.1, point 0.2, so 0.18. Are you following me? What is the
Yes,
value?
sir.
Yes, sir.
Yes, sir.
What is the value? 1.99 something, right?
Yes, sir. 1.94.
Okay,
1.994.
whatever it is. So you see that now you tell me that if this value is higher, that means you have a large difference between 60% finer particle and 10% finer particle. That means if Cu is higher, that means you have very large particle and very small particle because Cu is d60 by d10. Now, if this is higher, if this is higher, that means there is a large difference between D60 and D10. Am I right?
Yes, sir.
Yes, sir.
So you have very large particle and you have very small particle. That means this is uniform or non-uniform?
Non-uniform.
Non-uniform.
Non-uniform. This is non-uniform. Now, if you have similar type particle, similar size particle, similar size particle, similar size particle, then your D60 and D10 will be almost similar, and that's why it will be close to 1. Am I right?
Yes, sir.
This is uniform. Am I right? This is uniform. Am I right?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. Now, tell me one thing. If this is non-uniform, then you have very small particle. Am I right? So this gap will be filled out with smaller particles. Am I right?
Yes, sir.
Yes, sir.
This is non-uniform. But in uniform case, you don't have smaller particles to occupy this space. That means you have the pore space available for the water. Do you have that much pore space available for water here? No, because you have smaller particles occupying these sizes. So in an aquifer, would it be uniform or non-uniform?
Sir, it should be uniform.
Uniform. That means the CU value, coefficient of uniformity coefficient, would be smaller. Clear?
Yes.
That's why they are telling that the aquifer materials having low uniformity coefficient CU and high effective size. I already told you the larger particle will have larger pores, will have high hydraulic conductivity. Did you understand the meaning of this sentence now?
Yes, sir.
The aquifer materials, understandably, will have low uniformity coefficient, that means non-uniform, and high effective size, that means larger particles, and then it will have high hydraulic conductivity. And the best aquifer for screening is determined by comparison of the grain size analysis curve of the materials along the depth of the borehole. That means, oh, by the way, generally a material is classified as uniform if the uniformity coefficient is Cu is less than or equal to 2.0. So if Cu is less than or equal to 2, then we call it uniform. If Cu is greater than 2, we call it non-uniform. Clear?
Yes, sir.
Call it non. For aquifer, we need this. So anyway, what I was trying to say here is that, of course, uniformity coefficient gives you an idea of the porosity. If it's uniform, then you will have higher porosity. That means higher space for the water to occupy. But if it's non-uniform, then low space or low pores for the water to occupy. Clear?
Yes, sir.
So degree of the indicator of porosity. Uniformity coefficient is also an indicator of the degree of the porosity. So anyway, so what I was trying to say here, that what was our objective? Our objective is to determine the location of the aquifer. That's for that reason what we do, we bore holes. We bore holes and we bore holes. Okay, right? And we collect sample from here at different depth. We collect sample from here, we collect sample from here, we collect sample from here. And for each of the sample, we do grain size analysis and draw this graph. Are you following me?
Yes.
For each of
Yes,
the
sir.
sample. And then and we have the table also. We have the table also. And based on the table and the uniformity coefficient and the fineness modulus and the size of the particles, we determine that which particle has the properties that is suitable for an aquifer. Okay. Also, when we collect the sample, we'll see that the moisture or content of the sample, right? So that will also tell you that the location of the aquifer. Clear?
Yes, sir.
Sometimes, if you already have done this analysis, then for a nearby tube well, you don't need to do the analysis again because you already know that in nearby the aquifer location is 80 feet depth or 100 feet depth. So you can also do that for the others. Although there might be some drawdown with time, but you can have an approximation. Is it clear?
Yes, sir.
Yes, sir.
Okay. So in the next class, we will see how to use this grain size analysis curve to determine the location of the aquifer. Any questions, guys?
স্যার, আমরা স্যান্ড ট্র্যাপটা কি যখন স্ক্রিন বসাই তখন সাথে সাথেই ওটার পরেই স্যান্ড ট্র্যাপটা অলওয়েজ রাখি?
Yeah.
ওকে স্যার। স্যার, এটা কাজটা কি মেইনলি, মানে এটা স্যান্ড পার্টিকেল গুলোকে আহ, আটকিয়ে রাখে এই টাইপের?
Yeah, I mean, we don't give a screen here because eventually this will be blocked out by the sand particles. That's why we give it a solid pipe. That's it. Just sand trap.
ওকে স্যার।
Okay. Any other questions?
সলিড পাইপের ভিতর দিয়ে পানি যাবে কিভাবে?
We don't. Pani jabe na.
যদি
The water will not pass
ক্লোজ
through
থাকে।
here. Yeah, the water will pass through the screen
তো
also.
স্যার তাহলে টিউবওয়েলের পানি কিভাবে উঠবে, মানে
It,
এই সাইড তার উপর দিয়ে যাবে?
yeah,
ও
yeah. This is the screen. Okay.
ওকে স্যার।
We have the screen here, so water will enter through the screen and then extract it above. Okay. Any further questions? Okay
No,
then. Thank you very much. Have a good one and stay safe.